Hello again. In this lecture, we will take our first peek into the microscopic world as we wander through the historical development and understanding of the building block of all the elements, the atom. I learned in one of my numerous Western civilization courses that I took, somewhere around my third freshman year in college, about the great Greek thinker Plato, who spoke of 4 fundamental elements that make up all matter. He defined an element to mean the smallest division. These elements were described as earth, fire, water, and air, and were made from an infinitely divisible piece of matter called hyle. Hyle would shape itself into the 4 elemental forms. Backed up by his equally famous pupil Aristotle, the first table of elements became widely accepted, and the metaphysics of these 2 great philosophers would dominate scientific thought for over 2,000 years. They were not unique, though. There were other ancient tables of elements produced by other cultures. For example, the Chinese had similar metaphysical ideas and even had one additional element on their ancient table. They thought the fundamental elements were wood, fire, earth, metal, and water. There were dissenting voices in ancient Greece, though. Lysippus and Democritus believed that matter was composed of small, indivisible particles called atomos, which meant uncuttable. Obviously, these guys were crackpots, atoms. Ha! Who could believe that rubbish? On and on and on we marched through time, ignorant of the truth, but slowly hints and cracks began to show in Aristotle's and Plato's concrete world. Okay, enough of that. It's time to tear the wall down. In 1800, Alessandro Volta invented the voltaic pile. We now know this invention as a battery. A few weeks later, William Nicholson and Anthony Carlisle used the battery in a process called electrolysis to split water into something even more fundamental, hydrogen H and oxygen O gases. This experiment was strong evidence against old Plato and Aristotle's elemental table. How can water be an element indivisible and fundamental when it can be torn apart into even smaller bits? Also, in the amazing year of 1800, the great John Dalton presented an essay on the partial pressures of gases, a topic we'll look at later. The point is that in his musings and contemplation of the nature of gases, he proposed and finally finished in 1803 one of the most influential chemical theories up to that time. It's now known as Dalton's Atomic Theory and helped usher in the modern age of science. Remember, a theory is built on a great many laws and corroborated hypotheses. Dalton had read and studied all the literature by those before him and had made many significant discoveries of his own. From all this work, he was able to produce a significant and elegant culmination of the knowledge into this wide-ranging atomic theory. So let's write down the tenets of this new way of thinking about matter, this atomic theory. Elements are made of very small particles called atoms. Well, maybe Lysippus and Democritus weren't so crazy after all, huh? Atoms of an element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. Now, we're going to have to forgive Dalton. He didn't have an understanding of isotopes, which are the same element but are atoms with different mass due to a different number of neutrons. We'll learn more about isotopes later. Atoms cannot be subdivided, created, or destroyed. Now, he also didn't have an understanding of atoms being made of even smaller particles, electrons, protons, and neutrons. Again, a very forgivable mistake. Atoms of different elements combine in simple whole number ratios to form compounds. In chemical reactions, atoms are combined, separated, or rearranged. So we now have a more formal meaning to the terms atom and element. An element is as far as we can break down matter, by chemical means and is made up of identical atoms. This was demonstrated by Nicholson and Carlisle when they broke down water into the elements hydrogen and oxygen, elements that themselves can't be broken down any further by chemical means. Elements are bulk collections of identical atoms. Atoms are the individual building blocks of all elements. It was an amazing and courageous idea to propose a concept of a piece of matter that as scientists they could never hope to observe in their day. The first images of atoms were finally produced in 1981, 180 years later, utilizing a scanning tunneling microscope invented by IBM physicists Binning and Rohrer. Dalton redid the electrolysis experiment with water and assumed, incorrectly, that water was being split into an equal number of hydrogen atoms and oxygen atoms. He believed that water was the compound HO. He weighed the two gases he produced and found that the mass ratio of the H to O gases was 1:8. This result led him to believe an oxygen atom weighed 8 times more than a hydrogen atom. Remember, he was assuming that he was making as many oxygen atoms as hydrogen atoms in the electrolysis experiment, and it took a while to prove him wrong. In 1805, Joseph Louis Gay-Lusacc and Alexander von Humboldt conducted the gas reaction shown at constant temperature and pressure conditions. They found that to make a 1 volume of water, let's say 1 liter of water vapor trapped in a balloon, it took roughly an equal volume of hydrogen gas, but only a half of that volume of oxygen gas. Again, remember that all the gases are being held at the same temperature and pressure. This is a really cool result and the first semblance of what we now know as a modern balanced chemical equation. 1 volume of hydrogen gas plus half a volume of oxygen gas yields 1 volume of water gas at constant temperature and pressure. Now, it took the great Amado Avogadro in 1811 to interpret the results correctly. He surmised that for gases having the same pressure and temperature, that the volume was directly dependent on the number of particles. If 2 different balloons containing 2 different gases have the same volume at constant temperature and pressure, they both have the same number of particles. We call this finding Avogadro's Law. Now, we can check our good friend Avogadro's work based on what we have learned so far about the state of an ideal gas. We know the ideal gas equation of state is PV equals nRT, so let's verify that Avogadro was indeed correct. Now let's rearrange the equation first to solve for volume. We will then divide by both sides by pressure. Now we know that moles N equals the number of particles divided by Avogadro's constant, N divided by Na. So we'll replace the N with this ratio. Now we know that for Avogadro and Gay-Lusacc's particular system, pressure and temperature are being held constant. So we can gather R, T, P, and Avogadro's number into a parentheses and replace everything in the parentheses with a single constant. I choose the symbol C to represent this constant in this slide. It's clear from the resultant equation that the volume is directly dependent on the number of particles when pressure and temperature are constant, just as Avogadro surmised. Pretty smart for a guy who didn't have the equation of state of an ideal gas to guide him as we do. Looking back at Gay-Lusacc's and Humboldt's experiment and being armed with Avogadro's law, we see that it takes twice the number of hydrogen particles compared to oxygen particles based on volume to make water. Another way to state the result is that there must be a 2-to-1 ratio of hydrogen to oxygen atoms for each water particle that is produced. This result leads us to propose that water is actually a particle that is made of 2 hydrogen atoms and a single oxygen atom bonded together. Now, as you probably already know, we write this molecule of water as H2O. For you you very perceptive ones out there, you know there is still a problem. It turns out that Avogadro and friends lucked out somewhat. The element hydrogen is not made up of individual hydrogen atoms, but made up of individual particles containing two hydrogen atoms. We denote this as H2 and call this a diatomic gas. The lucky part is that oxygen, also in its natural occurring elemental form, is a diatomic gas, O2. So happily, the ratios and rationale in the previous slide still work out, but the correct way to think about Gay-Lusacc's chemical equation is 1 volume of H2 plus half a volume of O2 yields 1 volume of H2O at constant temperature and pressure, or simply as H2 plus half O2 yields H2O. Because we're dealing with ratios, 2H2 plus O2 yields 2 H2Os is just as correct. Like any mathematical equation, multiplying the chemical equation on the right and left side by a constant, in this case 2, doesn't change its meaning or mathematical equivalence. Other diatomic gases of some of the elements were later discovered. Nitrogen, N2, fluorine, F2, chlorine, Cl2, bromine, Br2, and iodine, I2. It's very important that we be familiar with and even memorize these diatomic gases, because we'll rarely find these elements in any other form in their natural gas phase. When someone mentions one of these chemicals, let's say chlorine gas, you're expected to know that what we mean is that chlorine gas is Cl2, not a Cl atom alone. The results of these experiments by Gay-Lusacc and the interpretation of Avogadro forced scientists also to reevaluate the relative mass ratio of hydrogen and oxygen atoms that were first proposed by Dalton. Since in water we have 2 hydrogens to 1 oxygen, Dalton's mass ratio of a hydrogen and oxygen atom should have been 1 to 16. Now, Dalton proposed that hydrogen should be the standard atom from which to compare the masses of all the other atoms and wanted to give it the value of 1. But later, the oxygen standard, which was easier to work with, was the preferred standard and was given a value of 16. Now, it turns out that using the oxygen standard was pretty good and was accurate to about 4 sig figs when compared to the modern standard we use today. Our modern standard is the carbon-12 atom, a specific carbon isotope that we set to 12 exactly. And again, don't worry, we'll look at isotopes in detail later. Anyway, scientists started tearing apart compounds they had in their labs, taking them all the way down to their base elements, discovering new elements, and then comparing the masses of all the different atoms they found to the standard oxygen atom set at 16. These comparisons of the atoms of elements to the standard oxygen atom resulted in a set of relative atomic masses for each element they discovered. The old term for these relative atomic masses was called atomic weights. And obviously, we know that mass and weight are not rigorously the same thing, but I still catch myself using the old term atomic weight at times. Now, rigorously, since we're doing mathematical comparisons or ratios of the atom's mass to the standard atomic mass of oxygen, the values we obtain are unitless. So the relative atomic mass is a unitless number associated with the atom. So what have we done to this point? We have separated ourselves from the ancient ideals of matter. We believe in the fundamental particles of all matter called atoms. We now have several elements isolated, and we know on average the relative atomic masses of the atoms of the elements. And as we continue to play with these elements in the lab, we also have a pretty good idea of their physical and chemical properties. Now, we define a chemical property as one in which we describe the reactivity of matter in a specific chemical process. Remember, in a chemical process, the substances change their chemical makeup and the arrangement of the atoms in the matter. Now, all we need is someone to gather up all the different elements that are now being discovered, arrange them in thoughtful ways, and begin identifying patterns that might turn up. Spoiler alert, it's the periodic table. We'll look at this wonderful discovery in another lecture. Catch you later.